The most massive objects in the universe are rarely the easiest to see. Often, astronomers locate them not by catching their light, but by feeling their gravity pull on the space around them. In the 1840s, astronomer Urbain Le Verrier noticed that Uranus was accelerating and decelerating in ways that Newtonian physics couldn't explain. He calculated the exact coordinates of an invisible influence pulling on the planet and told astronomers where to look. They found Neptune within 1 degree of his prediction. Astronomers have detected a similar gravitational discrepancy at the extreme outer edge of our solar system. Gravity is acting as a mathematical footprint. It suggests something enormous is moving through the dark, even if our current telescopes cannot perceive it. This diagram maps the trajectories of distant ice bodies called sednoids, trans-Neptunian objects with extremely elongated orbits. After billions of years of chaotic interactions, their orbits should be random. Instead, they are physically clustered in space. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown published a model showing that this clustering requires an external force. Their math points to a massive world hurting these ice bodies, the hypothesized Planet 9. But pointing an optical telescope at the predicted coordinates is not enough. Sunlight has to travel past 500 astronomical units. At that range, light follows the inverse square law, where the amount of sunbeams hitting an object drops off exponentially. Whatever faint light hits the planet has to reflect and travel that same distance back to our sensors. Planet 9 would effectively be a black object sitting against a black background. To find it, astronomers are moving away from reflected sunlight, rethinking the mechanics of the search. We can use the 2015 New Horizons flyby of Pluto as a baseline for what hides in the deep dark. This high-resolution map of Pluto's surface reveals shocking geological complexity. Inside Sputnik Planitia, the surface is covered in churning nitrogen ice cells and mountains of solid water ice. The probe even detected a blue atmospheric haze suspended high above the surface. If a dwarf planet is this geologically dynamic, a massive object like Planet 9 would likely be a complex, active world. These findings suggest the outer solar system is populated by dynamic worlds, requiring a search strategy that accounts for a planet in constant flux. Because Planet 9 is expected to be 600 times fainter than Pluto, scientists are searching for its internal heat using infrared sensors. This involves mining historical data archives from sky surveys like Akari and IRAS, satellites that mapped the sky using thermal imaging. They process this data using a method called shift and stack. By layering hundreds of images taken over several months, they can cancel out the noise of background stars, revealing faint, moving targets. Catching Planet 9 relies on this type of heavy computational data manipulation. The tool currently leading this infrared search is the Vera C. Rubin Observatory in Chile. The scale of its hardware is massive. It houses an 8.4-meter primary mirror paired with a 3.2 gigapixel camera, the largest digital sensor ever built for astronomy. This sensor has a field of view wide enough to capture 40 full moons in a single frame. The observatory maps the entire visible southern sky every few nights. It returns to the same patches of space 800 times over a 10-year period. This relentless repetition is designed to spot slow-moving targets across a massive galactic background. The observatory's software recently hit a milestone by successfully isolating a fast-spinning asteroid, 2025 MN45, from millions of static background stars. This test proves the automated systems can filter and track the type of faint, moving thermal signature predicted for Planet 9. With the detection systems verified, the search for a potential ninth planet has become a matter of raw processing time. Confirming this world would validate gravitational forensics as a tool for discovery and clarify the structural dynamics of our solar system's evolution.